Okay, we're going to start with a little recap of 6.1 and 6.2, just to clarify a couple things before we move on. So we started with the idea of approximating area under a curve. So why do we do this? If we think back to physics 20 and consider a velocity time graph, so if we do B and T, so generally this would be like meters per second, and this would be seconds or kilometers per hour an hour, something like that. And let's say we just have a constant velocity, okay? The y-axis represents a rate of change, right? So how position is changing with respect to time, okay? So how position is changing with respect to time. The x-axis represents time. So if we pick any 2 points A and B, so let's pick A and B, the distance traveled is equal to B times T, right? So unit analysis, we have meters per second times second. The seconds would cancel, we would just get meters, and that checks out. Okay. So the area under a curve tells us the accumulation of change over time. So, for example, if I ride my bike at 20 kilometers per hour for 3 hours, so if here's my time in hours, my velocity per hour. So if this is 1, 2, 3 hours, then I have accumulated 3 chunks of 20 kilometers, right? So 60 times 3, I've accumulated 60 kilometers of distance. So this area could be broken into smaller rectangles and summed. Okay, so we could call each of those smaller rectangles delta x. So for example, we could consider each hour, so that's what I've done, or each half hour or 15 minutes or whatever. We can call each chunk, as I said, delta x. As the number of rectangles approaches infinity, the width of each becomes infinitesimally small, right? So the more we get, the smaller and smaller and smaller and smaller they get. Okay, we write this in 2 ways. So this is 6.2. So we did the limit as n approaches it. That's not a limit. I got ahead of myself. Whoop-a-doo. We do the limit as n approaches infinity of the sum. So this is the sigma. Ooh. Zoom, focus, please. Oh, it doesn't want to, sad. There we go. So this is the sigma, that Greek letter sigma. That means we're gonna sum all of the things. We're gonna start at k being equal to 1, and we're gonna go to when k is equal to n. So it's gonna be the function of ck times delta x. Okay, so if we start at the value of k being equal to 1, their first rectangle, times the width of the rectangle, if we add all of those up and we say it's going to go until we have infinity, that's one way to write it. So this is like the height of the rectangle. This is the width of the rectangle. Or we can use this integral symbol. So this one's new. So it kind of looks like a stretched out S, so it's also a sum. So we're going to go of f of x times dx. So these two things are basically the same thing. So f of x is the function at a specific value, and then dx is that width. So this is the height again, and then this is the width. And we're doing that from two specific values, a and b. So we write those at the bottom and the top of this integral symbol. Okay, so this right here is a definite integral, meaning it has boundaries so the area can be known. Okay, so if we had something like this and our A was here, B was here, we can figure out what this area is. So we talked in 6.1 a couple different ways to approximate it, and once we get farther into this, we'll figure out easier ways to do that. We're gonna have little chunks, right? If we split these into a bunch of rectangles, so there are delta x's or our dx's, depending on which one we're doing. So that is a definite integral, as opposed to an indefinite integral. So like the integral of fx dx, because this time we don't have those boundaries. So this one doesn't have boundaries, so we don't know how much of the function to consider, right? So we don't know if we're like adding up all of the area forever, just a specific chunk, right? So how much of the function to consider. Okay, so integration or integral calculus in general is finding the area under the curve. To tie this in with derivatives, remember how we always talked about the relationship between position, velocity, and acceleration when we were talking about derivatives. So if this is all time, these ones are all t. And then our first one is position, then we have velocity, then we have acceleration. If our position graph looks like a parabola, okay, if the height of the parabola, if we think back to physics, the height of the parabola, we have 0 velocity, so that's this point. Here we've got a big positive velocity, then it's slowing down, slowing down, slowing down, slowing down. It hits 0, so we go boom. Then it's going to start speeding up with a negative velocity until it hits the ground. I'll give us that too. And then the acceleration generally is negative 9.81, so we draw that just as a straight line, right? See how this, we know that to get to this, we do the derivative. This line represents the slope of this line. Then the acceleration represents the slope of this one, so we do the derivative again, okay? How that's related to integration is basically the opposite. So if we go backwards, we are doing integration. So if finding the area under a graph of a velocity time function gives us position, it means that integration is the opposite of differentiation. In other words, integration is the same as finding the antiderivative, which we have done on multiple occasions. So remember when we were working backwards and we said, okay, we have a velocity equation and we want to find the position equation, and we were doing like the opposite, thinking through, okay, what would have given us this as the derivative and going that backwards thing, that was an antiderivative. And those are the cases where we would see that like plus C thing, right? So we're going to learn to calculate, but now we're going to use our calculator's function of integration. if it ever references this in the textbook, it references n int. So it's the same thing, but that's what they mean, okay? Okay, now we're going to start with the new stuff. So definite integrals, rules, and antiderivatives. So we're going to start with the definition. If the boundaries of integration are swapped, so if we're integrating from b to a, instead of usually we have a on the bottom, b on the top, if we're doing the opposite of a function, that's the same thing as the negative of the original. Okay, so if we're going backwards, so usually we go from a to b. If we went backwards, that's a negative integral. Okay, so basically it means now dx is negative, right? Because we're going, instead of going little bits that way, we're going little bits that way, right? That doesn't really help my notes, whatever. Hopefully you remember that when you see it. So the area becomes negative, okay? We can also conclude that if we start at A and we end at A and do the integral, we do the area under the curve, we're going to get 0, right? This makes sense because no width equals no area, right? If I have a box that's 0 centimeters high, I'm not going to be able to fit anything into that box. So we're going to use these rules of integrals. So if we figure out, so we don't know what the function is, but we do know that we're doing the area under a function. From 1 to 9, it gives us -1. From 7 to 9, it gives us 5. And then from 7 to 9 of a different function, notice how this one's h, these ones are both f, this one's 4. Okay, so we can use those bits of information to figure out the rest of this. So if we want to find each of the following, so if we want to do the integral from 1 to 9 of -3 times this function, this, just like in differentiation, if you see a constant in an integral, we can get that out in front. So this is basically like doing the integral of 3 times the function, which is, or sorry, -3 times the function, which is the same as doing -3 times that integral. So that -3 can come out in front. And then we can look at this. This is now exactly this. So we can substitute that -1 in, and we get a +3 for that particular statement. If we want the integral from 1 to 9 of f of x plus h of x, then this is the same. So I'm kind of going over the rules with examples here. This is the same as the integral from 1 to 9 of f of x dx plus the integral from 1 to 9 of h of x dx. So just like in differentiation, if we're doing the integral of 2 different things as a sum, we can split it into 2 separate statements. This one we can replace, now that's this, so we can replace that with a -1. This one, we don't actually know anything about from 1 to 9. We know from 7 to 9 is equal to 4, but we don't know how the function behaves and how the area is before that. So we're just going to leave this as 1 to 9. So the sum of the area under this curve from 1 to 9. So we're just going to leave that one like that. This next one, so we've got the integral from 7 to 9 of 2h of x minus 3f of x dx. So again, we're going to split it. So from 7 to 9, 2h of x dx minus, or sorry, I guess plus, from 7 to 9, -3f of x dx. So now we can pull the 2 out. And the -3 out. I guess then that can become a negative. So then we've got 2. This one we do know. So this is 2 times 4 minus 3 times -1. So 8 plus 3, we get 11. oh wait, not 11. This one's not the one. This is 5. Oops, poops. So 8 minus 15 gives us negative 7. Because that's this one that we're looking at from 7 to 9. This one, we've got from 1 to 7 of f of x dx. Now, if we think about this, so I'm just going to draw something random. This is like isn't actually what this graph looks like because part of it's negative. But I think this helps articulate my point. So if there's my x values, 1, 7, and 9, I know this whole area as a whole. So that's negative 1. So clearly part of this graph should have been under the x-axis. Oops. I also know this area by itself is 5. Okay, so I can figure out by knowing the whole and subtracting this guy what's left over. So that's going to be the same as the area from 1 to 9 of that function minus the area from 7 to 9 of that function. Then we can just plug in those numbers. So negative 1 minus 5 is equal to negative 6. Okay, so if you ever see a 1 and a 7 and you don't have those exact boundaries, think about what's the area as a whole look like? Can I subtract a chunk, generally the smaller chunk, from the bigger chunk? This one we've got from 9 to 7. So remember that this is equal to the negative version of the same thing with the boundaries flipped. So because we didn't have a from 7 to 9, or from a 9 to 7, but we do have a 7 to 9, we just make it a negative, and then we have a negative 4. So negative 4. On this one, we've got from 9 to 7 again. So I'm going to flip this whole thing, and I'm just keeping what's inside what we're actually doing the integral of constant. So I've said, okay, I need to change this from 9 to 7 to from 7 to 9, make it a negative, and then I can treat it as two different ones. So we've got negative from 7 to 9 of hx dx minus from 7 to 9 of f of x dx. So negative 4 goes in there, minus 5 goes in there. So we get negative 9 overall. Oh wait, there was already minus, so this should have been minus a negative. This one should have been a plus. My bad. It's a Sunday. I'm doing a video on a Sunday. I'm not in calc mode. Okay, so there's how we can use, or we could figure out like given values, or use given values to figure out unknown values. And I went through some of the rules. So the constant, if you've got sums or differences, you can split them up just like we did in differentiation. If we're talking about the average value of a geometric shape, this is also helpful in adding our area up. So if we sketch a graph of the following function and then find its average value using geometry, we can figure out the area under a graph with that. So we've got from negative 5 to negative 1. So let's actually draw in. There's negative 5. And try and make this as accurate as I can. So from negative 5 to negative 1, this is x plus 5. So that means that a negative 5 would be my x-intercept, and then a positive 5 would be my y-intercept, but it's going to run out at 4, the slope of positive 1, so it's going to look like that. Then we've got negative x plus 3, so our plus 3 would be our y-intercept, our positive 3 would be our x-intercept, and it's also got a slope of positive 1, so it looks, or sorry, negative 1 this time, so it looks something like that. Okay, so there's 4, there's 3. So if we figure out the area of this thing using a triangle formula, it would be base times height divided by 2. So the base, we've got 8 units across times 4 units up divided by 2. So 32 divided by 2, so 16 units squared. If we figure it out by using the average height times the base, we're going to see if that's the same thing. So if we look at each of these triangles independently, the average height, so the total height is 4, so the average height would be 2 on both of these guys. So average height is 2 units, right? So we do 4 minus 0 divided by 2, 2 units. If we do 2 times the width of the base, we also get 16 units squared. So these guys are the same thing. So that average height can save us a lot of times if we have lots of complex triangles, and that's what we are going to do whenever we have a trapezoid, and we'll talk lots about those later. Another theorem we need to know is the average mean or mean value theorem. So if f is integrable, no, it's integrable. That's what it is. I can't say that word. On a and b, so from a to b, its average or mean value on a to b is the average of this function is 1 divided by b minus a of, or times the integral of a to b of that function. So if we find the average value on of this function, so 1/2 x squared plus 3 on this in this domain 0 to 3, we would, a is 0, b is 3. That's our first thing that we need to identify. And then we're doing the average of the function is 1 over, it's always going to be b minus a, so 3 minus 0 in this case, times the integral from a to b of 1/2 x squared plus 3 dx. Remember, this is the function, and then we're adding up the little tiny bits of it. Okay, for now, we're just going to use the function of integration on your calculator. So you're actually just going to type that in, and it's going to spit out a number. And it should look identical to this on your guys' calculators. So then it's 1/3 times that value that you got off your calculator, which should be 13.5. So then I get 4.5. Calculus is always better with fractions, so we'll change it to 9/2. Okay, so does this value occur in the interval? Okay, we can check. So we can say, okay, is 9/2 going to be equal to y anywhere? So we plug that in as the value of y in the function. So then 1/2 x squared plus 3. So if this is solvable, then the answer is yes. So if we move the 3 over, divide or multiply both sides by 2, square root, we get x is equal to root 3. Okay, it should be positive or negative when we root both sides, but since we're talking about only from 0 to 3, then it's the positive. So this means that yes, it is on that interval. Okay, so the mean value theorem for definite integrals, if it's continuous on that, that part of the function, then at some point in that interval, this is going to be true. Okay, so we're going to find the average value of the following function on the interval 0 to pi. So we're doing y equals sine x, and we're doing the average on the interval 0 to pi. So a is 0, b is pi. So we're doing the average of the function is equal to 1 over, this is going to be pi minus 0 times the integral of 0 to pi of sine x dx. Okay, so in this again, we're going to use the function of integration in our calculator. So we're going to get 1 over pi times 2. So 2 over, if I do pi on the bottom of a fraction, I always make the fraction line squiggly too. 2 over pi. Okay, does this value occur in the interval? We set that equal, oh my gosh, set that equal to the y value and solve for x. So then x is going to be equal to sine inverse 2 over pi. Everything should be in radian mode, FYI. So this is 0.69. That is indeed in between 0 and pi. So yes. Okay. Okay. We can also use antiderivatives to calculate the definite integrals. So we can use the formula, the integral from a to x of this function is going to be equal to the antiderivative. So usually we write f, and if we're doing the derivative, we write f prime. But we don't always get given f prime. Sometimes we just get given f. And if we want to do, so this is derivative, this would be antiderivative. If we want to do the antiderivative of not f prime, we call it capital F. So this capital F means it's an antiderivative, okay? Anti-D, where where f of x is any antiderivative. The reason why it's any is, remember how there's tons of different constants, there's tons of different c values that could shift that thing up and down, where it would still give us the exact same slope value, but the function looks different. Okay, so in this case, we're just going to say any antiderivative. The easiest one is when c is equal to 0. Right, there hasn't been any vertical shift at all. Okay, so we take the top boundary, plug that in, bottom boundary, plug that in. Okay, so if we want to find it using the antiderivative, if we want to find the integral, so these are all definite integrals, right? They have boundaries. This is what we're going to do. We're going to figure out, okay, what is the antiderivative of this function inside here? Okay, so what do I need to take the derivative of to get sine? Okay, I know that the derivative of sine is cos, and the derivative of cos is negative sine. So if I ended up with a positive sign, I must have done the derivative of negative cos, okay? And then I'm going to have, I guess I didn't need the bracket there. I'm going to have my upper boundary plugged in first, and then minus the antiderivative, so negative cos of the lower boundary plugged in there. Okay, so cos of pi is -1 plus negative cos of 0 is +1. So -1 is 1, 1 is 1, so we get 1 plus 1 equals 2. Okay, so the area in between 0 and pi of this is 2. Okay, another one that we can do, so we're going to do the antiderivative of 3x squared. So we need to think, okay, what did that function start as if this is the derivative, right? So it would have been an x to the 3. That 3 would have dropped down, it would have gone to a 2. So this just is x cubed, okay? So we are going to have x, actually, I'm going to show you guys how we write this. So we're going to go x cubed from -2 to 1. So if you want to, like this one, I plugged the values in right away, but if you need to actually figure out the antiderivative first and then plug the values in, this is how we do it. Because we can't say it's the integral anymore. We can't leave that symbol there. We've already dealt with that. But this will say, this like line at the end is going to say, okay, from -2 to 1. Then we do our top value, so 1 cubed minus our bottom value, so -2 cubed is 1 minus -8, so we get 9. If we're doing the integral from -2 to 5 of 5 dx, we need to think about, okay, what was our function that this is the derivative, right? So this is going to be if we got the derivative as 5, it had to have started as 5x. And then we're going to evaluate that starting at -2 and going to 6. So we're going to take the upper value first and then subtract the lower value. So then 30, that turns into a plus 10, so 40. This one, we're going to have from 1 to 4 of -x to the -2. So we have to think about what our function was. If we have a -2 happening there, it must have started as x to the -1, right? Because then that -1 would have dropped down in front. Hey, there it is. And then this would have been decreased by 1 to -2. So that means our original function was x to the -1. We're going to start that at 1 and go to 4. So we're going to take, right, because if we ever have like two values, a, b, lower, higher, we're going to take this one, subtract this one to get this area in between. So we've got 4 to the -1 minus 1 to the -1. We could write that as 1 over 4 minus 1 over 1 if we wanted to. We could have gone to this like 1 over x from the 1 to the 4, right? If that makes it easier. So then we've got 1/4 minus 1, so we can change those both to 4s, so we end up with -3/4. So there's -3/4 of area there. Okay, one last application example. So the position of a particle at time t in seconds s is equal to the integral from 0 to t of the function x dx. So we're adding up all of the little bits, okay? So if we're getting the position from adding up all of the little bits, that means f of x is a velocity function, right? If we're doing the integral, we're adding up all the little bits under this line, and we're getting position, this has to be a velocity function. So this is velocity, and this is time. Here's the graph. You can tell I drew it in and then scanned it. What is the particle's velocity at time equals 3 seconds? So that should be like right on the nose there. So v equals 0. What is the acceleration of the particle at, is the acceleration of the particle at time equals 3 positive or negative? So if this is a velocity, if we want to know something about the acceleration, we're looking at the derivative, which means we're looking at the slope at that point. The slope here is positive. Right, so positive slope, which means it's a positive acceleration. It's going faster. What is the particle's position at time equals 3? So we would have to figure out how far this thing has been going. So this thing, if it's going in a negative, if it has negative velocity this whole time, basically if you considered positive to the right, basically it's just ending up to the left, right? If we figure out all of this area to figure out the position in the first 3 seconds, it's just going to be a negative area, and that just means maybe it's gone to the left instead of the right, or down instead of up, or whatever, okay? So we're doing the integral from 0 to 3 of the function. So I'm just going to use the area under the curve because I don't know the actual equation of this line to figure out the antiderivative. So I'm going to use area. So I'm just going to use base times height divided by 2. So base times height divided by 2. So base is 3, height is -6, divide that by 2, we get -9, okay? So that just means that it's gone 9 meters or kilometers or whatever it is. It's probably meters if it's per second, units to the left, right? The opposite of the positive direction. When does the particle pass through the origin? Okay, this would happen when position equals 0, right? So the starting point is at 0. So if it went -9 meters, so left 9 meters in the first 3 seconds, it has to go back. So if we went 9 meters, it needs to go back another 9 meters to be at 0, okay? So it needs to be at 6 seconds where the area above and below the x-axis are equal. So if we look at this, if you look at, here's 6 seconds, see how these two triangles are equal sizes? So we've got a height now of 6, a width of 3 again. So these two things have the exact same area. So this means it's gone to the left 9 and then to the right 9. So now it's back at the origin, okay? When is the acceleration 0? So if this is a velocity graph, the acceleration is going to be at the point where the derivative of this thing is 0. So it's going to be this point right here. Notice how it tells me my x-coordinate is 7, okay? X equals 7. Because we know slope equals 0. When is the particle moving towards the origin or away from the origin? Okay, so if we think about part D here, this first 3 seconds it's moving away from the origin. So between 0 and 3 seconds, it's moving away from the origin. In the next 3 seconds, it's moving towards the origin. In the next 3 seconds, so now see how this is all accumulating positive area. So that means that it's going in a positive direction that whole time. So then from 6 to, or sorry, when t is greater than 6, it's moving away from the origin. So it would just keep going that way. On which side of the origin does the particle lie at t equals 9? So the position at 9 is going to be the integral from 0 to 9 of f of x dx. But this is a really hard thing to calculate that area of. We don't know how to do that yet, and that's okay. What we need to think about is the positive area bigger than the negative area, or vice versa. If these two cancel out all this, then all of this positive area ends up being the displacement of this particle, okay? So it is going to be positive so because the area above the x-axis is greater than below. So that might be like right or up or whatever of the original position, but it depends on how positive and negative are going to be defined. And you guys know from Physics 20 that that can change depending on the question. So hopefully that all made sense. If it didn't, let me know. Send me any questions you have. We'll do a review Q&A tomorrow. For this section, you guys are going to be doing, let me just find it here. I know you guys have it, but I like to put it in the videos now. You're going to be doing page 294, number 5, 19, 21, 22, 25, 26, 48, and 50. Okay, so yeah, again, we'll review whatever questions you guys have tomorrow.